A billion miles from Earth, there exists a world where it rains. Not water, methane, where rivers have carved canyons hundreds of meters deep, where lakes stretch across thousands of square kilometers, where the sky is never blue, and the sun is just a dim smudge behind an impenetrable orange veil. This is the only place in the solar system, besides Earth, where liquid permanently exists on the surface. This is Titan. When Dutch astronomer Christian Huygens pointed his telescope at Saturn in 1655, he had no idea that the pinpoint of light he discovered would become one of the greatest mysteries of the cosmos. Huygens saw simply a moon, the sixth ever discovered after Jupiter's 4 Galilean moons and our own. He called it simply Saturn's moon. The name Titan came nearly 2 centuries later, when English astronomer John Herschel proposed naming Saturn's moons after the Titans, the mighty deities of Greek mythology, brothers and sisters of Kronos, whom the Romans identified with Saturn. The name proved prophetic. Titan is indeed titanic. Its diameter spans 5,150 kilometers. That's larger than Mercury, larger than Pluto. If Titan orbited the Sun rather than Saturn, we would call it a planet without hesitation. But size is only the beginning of this story. In 1944, something happened that changed everything we understood about this world. Dutch-American astronomer Gerard Kuiper, the same man after whom the Kuiper Belt is named, discovered something incredible. Using spectroscopy, he determined that Titan was surrounded by a dense atmosphere rich in methane. This was shocking. Until that moment, it was believed that only planets could retain significant atmospheres. Moons were just rocks, dead bodies hurtling through the void of space. And here was an atmosphere, thick, dense, opaque. Subsequent decades of research only deepened the mystery. It turned out that Titan's atmosphere wasn't just dense, it was denser than Earth's. 1.5 times denser. If you could stand on Titan's surface without a spacesuit, which is of course impossible for many reasons, the pressure on your body would be roughly equivalent to diving 5 meters deep in a swimming pool. Not deadly, just noticeable. This contrasts sharply with Mars, where the atmosphere is so thin your blood would boil within seconds. But what is this atmosphere made of? 95% nitrogen. The very same nitrogen that makes up 78% of the air you're breathing right now. Another 5% or so is methane. And it's the methane that makes Titan what it is. Methane on Titan plays the same role that water plays on Earth. It evaporates from the surface of lakes and seas, rises into the atmosphere, condenses into clouds, and falls back down as rain. This is a complete hydrological cycle. Only instead of water, it runs on hydrocarbon. Instead of H2O, CH4. But before we dive into Titan's methane seas, let's understand what makes this world so unlike anything else. What has hidden its surface from our eyes for nearly 400 years? The orange haze. When sunlight reaches the upper layers of Titan's atmosphere, remarkable chemistry begins. Ultraviolet radiation breaks apart molecules of methane and nitrogen. These fragments, radicals as chemists call them, are extremely reactive. They collide with each other, forming new, more complex molecules. Ethane, propane, acetylene, hydrogen cyanide, and most importantly, tholins. Tholins aren't a specific substance. They're an entire class of complex organic molecules that cannot be synthesized under Earth's oxygen-rich atmospheric conditions. Their name comes from the Greek word tholos, mud, murk, and it's a very accurate description. Tholins are a sticky, tarry substance of reddish-brown or orange color. On Earth, they can only be produced in laboratories that simulate the conditions of an ancient, oxygen-free atmosphere. On Titan, they form constantly by the trillions of tons. Tholin particles are tiny, about 0.2 of a micrometer in diameter. For comparison, a human hair is roughly 70 micrometers thick, but there are unimaginably many of these particles. They form a haze layer that begins at an altitude of about 500 kilometers and extends all the way to the surface. This layer is so dense that it completely blocks visible light. When the Voyager 1 probe flew past Titan in 1980, its cameras saw only a uniform orange ball. No surface details. Nothing. This was simultaneously a disappointment and an intrigue. A disappointment because scientists had hoped to see something. An intrigue because it became clear that beneath this haze lay an entire world we couldn't see through ordinary means. Titan's color isn't just an aesthetic feature. It tells the story of chemical processes that occurred on early Earth. For billion years ago, our planet probably looked similar. Orange haze of organic compounds. An atmosphere without oxygen. A chemical soup in which the first precursors of life were emerging. Titan is a time machine. A frozen snapshot of what Earth was before life appeared. But let's return to what lies beneath the orange shroud. For 3.5 decades after Voyager, humanity could only guess. Theories multiplied. Some believed Titan's entire surface was covered by a global ocean of liquid methane and ethane. Others proposed a solid ice crust. Still others, something in between. But no one knew for certain. Everything changed on January 15th, 2005. On that day, the Huygens probe, named after Titan's discoverer, accomplished what many thought impossible. It passed through 400 kilometers of orange haze and gently landed on the surface. For the first time in history, a human-made craft touched down on a body in the outer solar system. The descent took 2 hours and 27 minutes, and every second of that descent was filled with discoveries. At an altitude of 150 kilometers, Huygens began capturing the first surface details through the thinning haze. At 30 kilometers, the picture became clearer. The probe's cameras saw something that astonished even the boldest theorists. Winding dark lines resembling riverbeds. They descended from highlands toward lowlands. Branched, merged. This was a drainage system, just like on Earth. Only carved not by water, but by liquid methane. Bright areas turn out to be highlands covered with something like frost, perhaps frozen methane or ethane. Dark areas, lowlands, probably dried lake beds or seasonal river channels. And then Huygens touched the ground. Another surprise awaited. The surface was soft, not hard like rock, not liquid like an ocean, but something in between. The probe sank into it about 15 centimeters and stopped. The consistency was like wet sand or damp clay. Analysis showed the surface consisted of water ice. At minus 180 degrees Celsius, ice is as hard as granite, covered with a layer of organic sediments. Those same tholins that have been falling from the sky like orange snow for billions of years. Huygens operated on the surface for only 72 minutes. Its batteries weren't designed for more. But those 72 minutes changed our understanding of Titan forever. The probe transmitted 750 megabytes of data, photographs of the surface, temperature and pressure readings, atmospheric composition at various altitudes, the sounds of wind. Yes, Huygens recorded sounds from Titan, and you can find these recordings online. A quiet, sustained hum of an alien world. But Huygens was only part of the mission. The Cassini orbiter, which delivered the probe to Titan, continued working for another 13 years. And it was Cassini that discovered what became the main sensation, the methane seas. Cassini's radar could see through the orange haze. Radio waves passed where visible light was completely absorbed, and what the radar saw exceeded all expectations. On Titan's north pole lay a system of lakes and seas unlike anything else in the solar system. The largest received the name Kraken Mare after the mythical sea monster. Its area is approximately 400,000 square kilometers. That's larger than the Caspian Sea on Earth. Depth in some places exceeds 300 meters. Beside it, Ligeia Mare, with an area of about 130,000 square kilometers. And Punga Mare, around 60,000 square kilometers, plus dozens of smaller lakes scattered across the polar regions. But why specifically at the poles? Why not at the equator? The answer relates to Titan's climate. Yes, Titan has a climate, and it's remarkably complex. Titan orbits Saturn in approximately 16 Earth days. But it also has seasons, because Saturn's rotational axis and, consequently, Titan's orbital plane is tilted about 27 degrees to the orbital plane. That's slightly more than Earth's axial tilt. A year on Saturn, and correspondingly, a complete cycle of seasons on Titan, lasts about 29 Earth years. This means summer at Titan's North Pole lasts over 7 years, and winter also over 7 years. During these long seasons, sunlight, however weak it may be at such distance, unevenly heats different hemispheres. Methane evaporates where it's warmer, is transported by atmospheric currents, and condenses where it's colder. When Cassini arrived at Saturn in 2004, it was winter at Titan's North Pole. Lakes and seas were filled to the brim. The South Pole, where it was summer, looked almost dry, just a few small lakes. By the mission's end in 2017, the situation was beginning to change. Spring had come to the north, autumn to the south. Scientists suggest that over a complete seasonal cycle, methane gradually migrates from one pole to the other. And what about the equator? Titan's equatorial regions are an entirely different world. No lakes here, almost no liquid methane, but there are dunes. Titan's sand dunes stretch for thousands of kilometers along the equator. They run in parallel ridges up to 100 meters high, resembling the dunes of Namibia's desert in Africa. But the sand here isn't quartz. It's organic sand. Those same tholins that have been falling from the sky for billions of years, compressed and processed by wind into granules about 300 micrometers in size. The color of this sand is dark brown, almost black. If you could see Titan's equator without the haze, it would look like an endless chocolate desert under an orange sky. Winds on Titan are gentle, about 1 meter per second at the surface, but in the dense atmosphere, that's enough to slowly, over millennia, shape these giant sand waves. Between the polar seas and equatorial dunes lie the middle latitudes, and they may be the most intriguing. Here, Cassini discovered structures scientists called labyrinthine terrain. These are networks of canyons and valleys cut into Titan's icy crust. Some resemble Earth's karst landscapes, those formed when water dissolves limestone. On Titan, methane plays water's role, and organic deposits, or perhaps even water ice itself, plays limestone's role. There are mountains here too, not as high as on Earth or Mars, 3 kilometers above mean surface level at most. But for a world whose crust consists of water ice, that's considerable. The origin of these mountains remains a mystery. Perhaps they result from cryovolcanism, eruptions where liquid water mixed with ammonia reaches the surface instead of molten rock. Perhaps from tectonic activity in the ice crust. Or perhaps from ancient impact events whose traces have been nearly erased by erosion over billions of years. And here we come to one of Titan's most remarkable aspects: erosion. On most solar system bodies, surfaces preserve traces of ancient catastrophes virtually forever. The moon is covered with craters billions of years old. Mercury, too. Even Mars, despite its dust storms, preserves ancient relief. But on Titan, there are almost no craters. Cassini found fewer than 100 impact craters on the entire surface. For comparison, our moon has millions. This means Titan's surface is geologically young, no more than a few 100 million years old. Something constantly renews it. Something erases traces of ancient impacts. Three processes work together. First, atmospheric erosion. Wind and methane rain slowly destroy relief. Smooth highlands fill lowlands with sediments. Second, cryovolcanism. If water-ammonia eruptions really exist on Titan, they could cover old surfaces with fresh material. Third, tectonics. Titan's ice crust may be in constant slow motion, like Earth's lithosphere. But all this is just the surface. Literally, because beneath the orange haze and methane seas, beneath the ice crust, something even more intriguing lies hidden: a subsurface ocean. Cassini's gravimetry data showed that Titan isn't a uniform ball of ice and rock. Its internal structure is more complex. Beneath an ice crust 50 to 100 kilometers thick lies a layer of liquid water. A real ocean, possibly hundreds of kilometers deep. The temperature of this ocean is around minus 20 degrees Celsius. Fresh water would have frozen long ago at such temperatures. But Titan's ocean probably contains large amounts of ammonia, an antifreeze that lowers the freezing point. And here Titan's story becomes truly exciting, because liquid water is a key ingredient for life as we know it. Enceladus, another moon of Saturn, also has a subsurface ocean, and geysers ejecting water vapor into space contain organic molecules and possibly even molecular hydrogen, which could serve as an energy source for microorganisms. Europa, Jupiter's moon, has a similar ocean and is considered one of the prime targets in the search for extraterrestrial life. Titan stands out even among them because it has something no one else in the solar system has: two potential habitats for life. First, the subsurface water ocean. If there are energy sources there, geothermal heat from the silicate core, for example, and if the ammonia water environment isn't too toxic, life could have originated and existed there for billions of years, completely isolated from the surface. Second, the methane seas on the surface. And here things get truly strange. Life on Earth is based on water. Water is the universal solvent in which biochemical reactions occur. Water is part of every living cell. Without water, no life. At least, that's what we've always believed. But what if that's not the only path? What if life could be based on a different solvent? Methane is also a liquid under certain conditions. On Titan, those conditions are met. Methane there plays water's role. It flows in rivers, fills lakes, evaporates, and falls as rain. Theoretically, purely theoretically, biochemical reactions could occur in it too. In 2015, a group of scientists from Cornell University published a paper that rocked the scientific community. They modeled a hypothetical cell membrane that could function in liquid methane. On Earth, cell membranes consist of phospholipids, molecules with one end that loves water and another that repels it. Such molecules wouldn't work in methane, but the researchers found other compounds, nitrogen-containing organic molecules that can self-organize into membrane-like structures, specifically in liquid methane. They called these hypothetical structures azotosomes. Do azotosomes exist on Titan? We don't know. Does life exist in the methane seas? We don't know. But the very possibility, the very thought that life could be so unlike anything we know, forces us to look at this orange world anew. There are indirect hints too. A hydrogen deficit has been detected in Titan's atmosphere near the surface. Hydrogen forms in the upper atmosphere and should sink downward, but there's less than expected. Where does it go? One explanation is purely chemical. Hydrogen binds with organic molecules on the surface. Another is more thrilling. Something consumes it. Something breathes hydrogen the way we breathe oxygen. Similarly, an acetylene deficit has been found on the surface. Acetylene is a high-energy compound. If methanogenic organisms existed on Titan, they could obtain energy by reducing acetylene with hydrogen to form methane. This is pure speculation, but speculation based on real data. Let's pause for a moment and appreciate the scale of what we're discussing. A world a billion miles from the sun's surface temperature of minus 180 degrees. Not a drop of liquid water on the surface. And yet, the possibility of life. Possibly two completely different forms of life on one body. Water-based in the depths and methane-based on the surface. If this is confirmed, and it can only be confirmed or refuted through direct investigation, it will be the greatest discovery in human history, because it will show that life isn't an accident, not a unique phenomenon that arose once on one planet. Life is a universal process that finds a way to emerge wherever there's the slightest possibility. But for now, these are hypotheses. Let's return to what we know for certain, to what Cassini's and Huygens' cameras saw, to the methane seas. Kraken Mare, the largest of them, lies between 70 and 80 degrees north latitude. Its coastline is carved with bays and peninsulas. Islands protrude from the dark liquid surface. Some of these islands are the size of Earth countries. Cassini observed them changing over time, perhaps due to sea level fluctuations, perhaps due to waves or ripples on the surface. Yes, there are waves on the methane seas. They're small, a few centimeters high at most. Gravity on Titan is weak, only 14% of Earth's, and the dense atmosphere effectively dampens surface oscillations. But they exist. Cassini's radar detected their reflections. Tiny waves on a hydrocarbon sea under the orange sky of an alien world. The composition of the seas isn't uniform. Kraken Mare and Ligeia Mare appear to contain mostly methane with some ethane, about 60 to 70% methane. But Punga Mare and some smaller lakes are richer in ethane. Ethane is heavier than methane and less volatile. Perhaps in lakes that are less frequently refreshed by rain, methane gradually evaporates, leaving a more concentrated ethane solution. The clarity of these seas is remarkably high. Liquid methane is nearly transparent to radio waves, which allowed Cassini to measure depth. In some places, the radar could see the bottom at over 150 meters deep. This means if you could dive into Kraken Mare with a flashlight, theoretically, in a suit capable of withstanding liquid nitrogen temperatures, you would see the bottom. What's on that bottom? Probably sediments, the same organic compounds that cover Titan's entire surface. Perhaps there are structures resembling Earth's mudflats. Perhaps underwater canyons carved by currents. We don't know. No craft has yet descended into a methane sea. But that may change. In 2019, NASA approved the Dragonfly mission. This will be a rotorcraft, something between a helicopter and a drone, that will fly through Titan's dense atmosphere. Launch is scheduled for 2028. Arrival at Titan, 2034. Dragonfly will hop from place to place, covering dozens of kilometers with each flight. Its goal is studying surface chemistry, searching for prebiotic molecules, understanding processes that could lead to life's origin. Over its nominal mission of 2.5 Earth years, less than 2 months in Titan time, the craft will cover more than 170 kilometers. That's more than all Mars rovers combined throughout the entire history of Mars exploration. Why a rotorcraft? Why not a rover, not a lander? The answer lies in Titan's unique conditions. Dense atmosphere and weak gravity make flight remarkably efficient. Lifting a kilogram of mass into the air on Titan requires roughly 40 times less energy than on Earth. Dragonfly's batteries will charge from a radioisotope thermoelectric generator, the same type that powered Cassini and currently powers the Curiosity rover on Mars. A few hours of charging, and the craft is ready for its next hop. Dragonfly won't explore the methane seas directly. Its trajectory passes through equatorial regions, but it will study the organic dunes, craters, possible cryovolcanic structures. It will search for molecules that could become building blocks of life. Amino acids, nucleotides, sugars, everything we find in meteorites, but in much larger quantities. There are other proposals too. A submarine concept for Kraken Mare is being developed at Johns Hopkins Applied Physics Laboratory. This will be the first craft in history to explore an extraterrestrial ocean from within. Picture it, a submarine slowly descending into the black depths of a hydrocarbon sea. Its spotlights illuminate the bottom covered with organic silt. Sonar scans the surrounding space. A manipulator takes soil samples. The technical challenges are colossal. How do you transmit data from depth through an opaque atmosphere? How do you control a craft when signal delay from Earth to Titan is 70 to 90 minutes one way? How do you power a machine operating at liquid nitrogen temperatures? But these problems are solvable. And someday, perhaps in your lifetime, a submarine from Earth will sail through a methane sea under Titan's orange sky. For now, let's return to the atmosphere. We talked about tholins and the orange haze, but that's only part of the story. Titan's atmosphere is a complex chemical laboratory that has been running nonstop for billions of years. In the upper layers, at about 1,000 kilometers altitude, solar ultraviolet radiation and a stream of charged particles from Saturn break apart nitrogen and methane molecules. Ions and radicals form, particles with unpaired electrons ready to react with anything. They collide with each other, forming the simplest organic compounds: ethane, propane, acetylene, ethylene. These compounds descend lower into the stratosphere, the layer between 200 and 300 kilometers altitude. Here, chemical reactions continue, but now without ultraviolet participation. The tholins themselves serve as catalysts. Their surfaces are active and can accelerate transformations of organic molecules. Lower still, in the troposphere, the layer from the surface to about 50 kilometers, condensation occurs. Methane and ethane form clouds. Yes, Titan has clouds, and Cassini observed their movement, formation, dissipation. They appear as whitish patches against the orange haze background. Rain falls from them. Methane rains on Titan aren't frequent events. At least, not everywhere and not always. Equatorial regions appear almost desert-like. Rain may not have fallen there for thousands of years. But when it does happen, these are events of epic proportions. In 2010, Cassini observed a storm front over Titan's equator, a massive cloud system stretching thousands of kilometers. After it passed, dark spots appeared on the surface, wet areas where methane rain had fallen. Over several months, these spots dried and disappeared. The methane evaporated back into the atmosphere. Picture this rain. Methane droplets, larger than Earth's due to low gravity and dense atmosphere. They fall more slowly, about 1.5 meters per second instead of Earth's 9, falling through orange haze that never clears, reaching the surface, collecting into streams, flowing toward lowlands, dissolving organic sediments, carrying them along, filling lakes, and then slowly, over months and years, evaporating back. This cycle has continued for billions of years, since Titan formed from the gas dust cloud around young Saturn. Since its atmosphere reached sufficient density to retain liquid methane. 4.5 billion years of chemical evolution, preserved by cosmic cold. And here's another mystery. Methane in Titan's atmosphere should have run out long ago. Ultraviolet destroys it. It transforms into more complex compounds that settle on the surface and don't return to the atmosphere. Calculations show that at current destruction rates, all atmospheric methane should have disappeared within 10 to 50 million years. That's an instant by geological standards. It's still there. Something replenishes the methane supply. But what? One hypothesis is cryovolcanism. If methane clathrate reservoirs exist in Titan's interior, compounds where methane molecules are trapped in a crystalline lattice of water ice, they could periodically release methane to the surface. Volcanoes erupting not lava, but methane. Cassini found several structures resembling volcanic cones, but obtained no direct evidence of eruptions. Another hypothesis is serpentinization. This is a geochemical process where water reacts with iron-magnesium minerals, producing hydrogen. Hydrogen, in turn, can react with carbon dioxide or carbon-containing compounds, producing methane. On Earth, serpentinization occurs at mid-ocean ridges. On Titan, it could happen in the contact zone between the silicate core and the subsurface ocean. The third hypothesis is the most intriguing. Life. Methanogenic organisms in the subsurface ocean could produce methane as a metabolic byproduct. Some of this methane could seep through the ice crust to the surface. This hypothesis is speculative, but doesn't contradict known data. Most likely, all three mechanisms are at work, or some two of them, or even something entirely different that we haven't thought of yet. Titan knows how to surprise. Now let's talk about what the world would look like through a traveler's eyes. Picture yourself descending through Titan's atmosphere in a ship of the future. What would you see? At 1,000 kilometers altitude, the darkness of space studded with stars. Saturn, huge, majestic, with rings visible at an angle, occupies a significant portion of the sky. The sun from here is a bright star, but it's already apparent that it's a disk, not a point. At 500 kilometers altitude, you enter the upper haze layer. The sky begins to lighten. An orange tint appears on the horizon. Stars fade, then disappear entirely. Saturn is still visible but blurred, indistinct. At 200 kilometers altitude, you're completely immersed in orange fog. Visibility extends several kilometers in all directions. There's no sense of up or down, the same orange light everywhere. The sun is a blurred bright spot casting no shadows. At 100 kilometers altitude, the haze begins to thin. Layers appear, darker and lighter bands running parallel to the horizon. These are haze layers with different particle concentrations. At 50 kilometers altitude, you emerge from the main haze layer. Below you, more haze, but surface contours are now visible through it. Dark areas, lowlands. Bright areas, highlands. In the distance, something glistening, perhaps a lake. At 10 kilometers altitude, details become clearer. You see riverbeds dry, winding lines on the surface. You see dunes, parallel ridges stretching to the horizon. You see craters, rare, half erased. At 1 kilometer altitude, you can distinguish individual rocks, blocks of water ice scattered across the surface. Tholins cover everything in an even orange-brown layer, smoothing sharp edges. And then, landing. You're on Titan. The sky above is orange. Not blue, not black, orange. The sun is a dim spot barely casting shadows. Its light is roughly 1,000 times weaker than on Earth. Noon on Titan is lit about as brightly as Earth's twilight, but with an orange tint. The horizon is closer than on Earth due to Titan's smaller radius. It blurs into haze just a few kilometers away. The surface beneath your feet isn't solid rock. It's a layer of organic sediments over water ice, soft like wet sand. Every step you take leaves a clear imprint. Temperature, minus 179 degrees. Your suit heats from within, and it's surrounded by a cloud of condensing vapor. Your own heat creates local fog around you. Silence is nearly complete. The atmosphere is dense, sound travels well through it, but there are almost no sound sources. Perhaps a faint whisper of wind. Perhaps distant rumbling if a cryovolcanic eruption is happening somewhere. But mostly silence. If you approach the edge of a methane lake, you'll see a dark, almost black surface. Liquid methane doesn't reflect light like water. It's more transparent, less shiny. Waves are almost absent, slight ripples from wind. If you lower your suited hand in, you won't feel cold through the insulation, but you'll see liquid slowly flowing around the glove. It's less viscous than water, more fluid. And if you look up at a certain time of Titan's day, when Saturn is above the horizon, you'll see something incredible. Through the orange haze, blurred but recognizable, looms the giant. Saturn occupies about 11 degrees in Titan's sky, 20 times larger than the full moon in Earth's sky. Its rings, a thin band, visible at an angle depending on Titan's orbital position. Saturn never fully sets. Titan rotates synchronously, always showing the same face to it. This view has never been seen by any human. So far, only robot cameras. But someday, perhaps, someone will stand where you mentally stand now, looking at the orange sky, at the methane sea, at distant Saturn in its ring of rings, and thinking about how remarkable the universe turned out to be. Now, let's talk about time on Titan. The concept of day here is ambiguous. Titan orbits Saturn in 15.945 Earth days, roughly 15 days and 23 hours. This is its orbital period. But since Titan's rotation is synchronized with its orbit, it always shows the same face to Saturn. Its sidereal day equals its orbital period. 16 Earth days from sunrise to sunrise. But wait, light on Titan's surface is so scattered by haze that the concepts of sunrise and sunset almost lose meaning. Illumination changes gradually. There's no sharp boundary between day and night. Twilight always. As for temperature, it barely changes. Minus 179 at the equator, minus 183 at the poles. The difference between day and night, 1 or 2 degrees. The dense atmosphere is an excellent thermostat, efficiently redistributing heat. Seasons, as we already discussed, last about 7 Earth years each. The difference between summer and winter at the poles, a few degrees, plus changes in cloud distribution and possibly precipitation. For comparison, on Earth, seasons define our entire lives. Agriculture, migrations, holidays, everything is tied to the changing of seasons. On Titan, a hypothetical inhabitant would barely notice this change. The meaningful rhythm for them wouldn't be seasons, but the 16-day cycle of Titan's day. And perhaps even that would be unnoticeable due to perpetual twilight. Let's move to a topic that excites everyone thinking about the distant future. Can Titan be colonized? At first glance, this is madness. Temperatures at which liquid methane flows in rivers. An atmosphere without oxygen. A distance that current rockets take 7 years to cover. No useful minerals in the conventional sense. Instead of iron and copper, there's ice and organics here. But let's look at it differently. Dense atmosphere means protection from cosmic radiation. On the Moon or Mars, colonists would be exposed to constant radiation. On Titan, the atmosphere blocks almost everything. Low gravity means less strain on the body. Yes, weightlessness is harmful, but 1/7 of Earth's gravity, like on Titan, might be sufficient for health, though this isn't proven. Abundance of organic compounds means resources for chemical industry. Titan is literally covered with hydrocarbons. On Earth, we extract them from underground, but here they lie on the surface. Methane and ethane are fuel. Primitive internal combustion engines could run on Titan's air if you add an oxidizer. Moreover, methane can be used as rocket fuel for returning to Earth. Water ice is water. Melt it, and you have water for drinking, for agriculture in enclosed greenhouses, for obtaining oxygen through electrolysis. And one more argument that's rarely mentioned. Flight on Titan is an almost trivial task. Remember we said that dense atmosphere and low gravity make flight 40 times more efficient than on Earth? Colonists on Titan could fly on the simplest craft, literally bicycles with wings and a propeller. A person in a suit with small wings could glide for kilometers. Air transport would be the foundation of civilization. Of course, all this is dreams of the distant future. First, we need to learn to live on the Moon, then on Mars, then in the asteroid belt, and only then, perhaps centuries from now, on Titan. But dreams matter. They determine the direction of movement. And Titan is a worthy target for dreams. Let's return to the present, to what we've learned and what we still don't know. We know that Titan is the only body in the solar system besides Earth with a dense nitrogen atmosphere. We know that liquid seas exist on its surface. We know that its chemistry resembles processes that could have occurred on early Earth. We don't know if there's life on Titan. We don't know the exact composition of the subsurface ocean. We don't know what replenishes atmospheric methane supplies. We don't know how deep the methane seas are or what lies on their bottoms. Every answer generates new questions. That's how science works. That's how knowledge works. Titan isn't a destination, but a door. A door to understanding what life is, what a planet is, what possibility is. And that door is opening wider. Dragonfly will launch in 2028. It will reach Titan in 2034. By then, a new generation of scientists will have grown up for whom Titan's orange world won't be exotic, but an object of daily research. They'll analyze surface data, search for biomarkers, map dunes and lakes, debate hypotheses, and build new theories. And then, perhaps, the submarine will fly, and rovers, and, who knows, the first humans. Titan's story is just beginning. We know less about it than early cartographers knew about Australia, less than early seafarers knew about ocean depths. Before us lies an entire world awaiting its own Columbuses and Magellans, its own Darwins and Humboldts. And this world is orange, wrapped in haze of organic molecules, with rivers and seas of liquid methane, with dunes of hydrocarbon sand, with a sky that's never blue. Titan,